Hello everyone, welcome to all of you in my YouTube channel. Today, in this short video, I am going to explain about the kinetic energy, average kinetic energy of the gas molecules. Okay, I am going to discuss the average translational kinetic energy of the gas molecule. So for this, suppose that let us consider for 1 mole of the gas, for 1 mole of the gas, from the ideal gas equation we know that PV equal to nRT. So for 1 mole N will be 1, that's why PV equal to nRT, PV equal to RT. Again, from the kinetic theory of gas, we know that P is equal to 1 by 3 rho c square. That's we know. We know that P is equal to 1 by 3 rho c square. This is the mean square velocity. Okay. So in place of this rho, we can actually write m by m divided by v. M divided by v. So that's why this pressure equal to 1 by 3 m divided by v c square to the power bar. So now what we get, if we cross multiply this, we will get PV is equal to 1 by 3 mc square bar, mean square. This velocity is called mean square velocity. Now we can equate the equation 1 and 2. After equating, we will get PV are the same in the left hand side, and in the right hand side we will get 1 by 3 mc square bar is equal to RT. And if by the cross multiplication, we will get mc square is equal to 3RT. Now, as we know that kinetic energy means 1 by 2 mv square. So that's why here capital M means the total mass of the gas. Total mass of the gas, and c square means c square bar means the mean square velocity. So if we let us multiply by 1 by 2 on the both side, then we get 1 by 2 mc square bar equal to 3 by 2 RT. So this is actually the kinetic energy of for 1 mole of gas actually, because we have already considered 1 mole of the gas. So that's why 1 by 2 m means total mass of the gas, total mass of 1 mole of the gas, we can say. For 1 mole of the gas, the total mass is capital M, and c square bar equal to 3 by 2 RT. So it implies that kinetic energy per mole of gas is equal to 3 by 2 RT. This implies that, what does it mean? It means that kinetic energy is directly proportional to the temperature. If the temperature increases, the kinetic energy of the gas molecule also increases. So this formula is utilized when we want to find the kinetic energy for 1 mole of the gas, or we can say in the numerical problems, kinetic energy, total kinetic energy of the gas. Now if we want to calculate the kinetic energy per molecule of the gas for 1 molecule, if we want to find the kinetic energy for 1 molecule of the gas, then actually what we can write, as we already have this relation 1 by 2 mc square bar is equal to 3 by 2 RT. So this m means the total mass of the gas. Now what actually we can do here is that capital M is equal to m small m into the total number of the molecules, small m into the total number of molecules. But as we consider that 1 mole of the gas, and we know that for 1 mole of the gas, the total number of molecules is equal to the Avogadro's number, 6.023 10 to the power 23. That's why 1 by 2, in place of capital M, we can actually write small m times Na, because in general we actually write m into n, but in this case, as there is 1 mole of the gas, for 1 mole of the gas we know that the number of the molecules will be equal to the Avogadro's number. That's why m times Na c square bar equal to 3 by 2 RT. Now remove this Na from here and take this in the right hand side. Then what we will get in the left hand side means 1 by 2 mc square bar. 1 by 2 mc square bar equal to 3 by 2 R by Na times T. So here R divided by Na means Boltzmann constant K, that is represented by the K. K means Boltzmann constant. R means universal gas constant. If the universal gas constant is divided by Avogadro's number, we will get the Boltzmann constant. So 1 by 2 m, small m means the molecule of the mass of one molecule, mass of the molecule, and c square means the mean square velocity. The mean square velocity is same for each molecule. That's why we can say 1 by 2 mc square is the kinetic energy for one molecule of the gas. Kinetic energy for one molecule of the gas. Then we get the kinetic energy for one molecule of the gas is 3 by 2 RT. 3 by 2 KT, sorry, where K is the Boltzmann constant. So this is very important in numerical problems. Basically, when you have to find kinetic energy for 1 mole of the gas or total kinetic energy of the gas, you should have to use the formula 3 by 2 RT. But in the case when you have to find the kinetic energy for one molecule of the gas, in such cases you have to write this formula 3 by 2 KT. Okay, so this much for today. Thank you very much.